Welcome back. Today we're going to talk about one of the, I think, very strange parts of orthogonal projections, and that's the projection operator. So the idea behind the projection operator is, well, let me bring it up. Let's start first, assuming that we have some function x that's in some vector space S, and back to our problem. We've spent a long time, many times, coming back to the same problem, and we'll continue to do so because it has a lot of useful applications that we'll see going forward. So we want to find x hat in some subspace that is closest to x. And where, of course, t is a subspace of S. Okay. We've already seen now that if we have an orthobasis, and we're going to talk about what to do if we don't have an orthobasis later. But for now, if we have some orthobasis for t, then we know that x hat is equal to the sum of the projection onto each of the basis vectors times that basis vector. Now, just as a word of caution, this particular function, this representation, only holds true if we have an orthobasis. We can still represent x as a linear sum of basis vectors times some alpha or a or whatever you want your coefficient to be, but in that case we have to find it by first finding the projection and then multiplying it by the inverse of the Gramian. So this is an orthogonal projection of x onto t. And so we're going to say there's an operator that does this. Call it PT, projection onto t, and this would be our projection operator. In general, PT of x is then going to be the sum, n equals 1 to n, exactly what we've seen here. So Vn, so on and so forth. Okay, so let's look at some of the properties of this. Of PT. First one, for any x in t, PT of x is equal to x. So we can actually prove this pretty simply. Yeah, I'll go through this just for the exercise. We show it by writing that x is equal to the sum over n x Vn like so. then pt of x will be pt of, actually, I got ahead of myself. We're going to start by assuming we have no idea what these alphas are. Wink, wink. And so now we do this. We do the projection of alpha times v. So why can we write this if we don't know what the alphas are? It's because we already know that Vn is a basis for t. And we already know that if we have a basis for t, we can write the vector as a linear sum of the basis vectors. Okay, so the pt operator now comes into play. So we'll have a different sum of the index here. And now this is going to be where we used to have an x, we're going to have our n equals 1 to capital N, alpha n, Vn, and we project that onto VL, and we multiply it by VL. And using the laws of inner products, we can essentially take this sum out. It's on the left hand side, so we don't even have to worry about conjugates if there are any. And we get Vn VL times VL. And we know that this is equal to 1 for L equals N because it's an orthonormal basis, and 0 for L not equal to N. So one of those sums is redundant, and we just get N equals 1 to N of alpha. I don't know how that 8 appeared right in the middle there. I think I bumped my... Well, that's pretty cool. There we go. On the keypad, I'll take it off. Okay. That's equal to the sum of n equals 1 to n alpha VL, and we've already defined that as x. So what we found is, regardless of what x is, as long as x is in t, then when we do our projection, we get x back. Well, the next property follows directly from that, and that is that pt is idempotent. That means essentially that pt squared, or pt operating on pt, is equal to p. So all of this makes sense, I think, so far, because we have something that takes x and throws it into t, and if it's already in t, it just throws it right back to the same spot. It gets interesting, I think, when we actually define this as a matrix, as a matrix projection, because you end up with a matrix when multiplied by itself is equal to itself. Okay, so while I was talking about other things, we can define Q is equal to I, or the identity operation, minus PT. And so essentially we know that x minus pt of x is something we've been talking about now for days. We can represent that using our standard example, if this is x right here, then I'm drawing it small, I'll make it bigger, then x hat is going to be there, and this quantity right here is x minus pt of x. So what does that tell us? Well, pt is going to be the projection onto t, and x minus pt has got to be orthogonal to it. So I realized I didn't offer a complete proof of that statement, but this is one that I think you can look at and convince yourself that this is indeed the case. Give it a shot, see what you think. X minus pt. How would you find out if it's orthogonal? Well, you would have to validate that x minus pt of x projected onto x was equal to 0. And you could go through and do that on your own. It's a good way to see how. In fact, I recommend pausing now and giving it a shot. So, in fact, we can continue on and say qt of x can be constructed similarly to pt. In other words, all we do is we need an orthobasis for the subspace of S that is orthogonal to T. In other words, so we've defined some other subspace, and we're gonna call that T with a little orthogonal thing up there, like that. Okay, so what is that? Basically, T, the orthogonal subset to T, is going to be equal to S, and then we're going to remove T. So that's how we call it. We actually don't remove all the elements because we have to have the 0 element in both, right? But other than that, remove it. Another way of looking at this is that S can be built up as a direct sum. S is equal to T plus the orthogonal subset. Okay, well, this introduces some interesting new little properties we want to talk about. One consequence of that is, let's put in the math, but I'll kind of talk through what it means. We can pick any x and y in S and use these projections we get pt of x 1 minus or I minus pt of y. So this is our QT operator right there. But that's just equal to, once again, the projection of x onto t with y minus the projection of y onto t. So what's going on here? We've essentially taken any x and y and we said we only want to keep the part of x that's in t, and we only want to keep the part of y that is not in t. And so the result is those are in orthogonal subspaces, and we get that that's equal to 0. And we can do this in other ways as well, where we have pt x comma y. Well, what is this going to be? Well, this would actually be pt of x with, and here we would have y minus pt of y plus pt of y. So all of that is just another way we've added and subtracted the same quantity. So it's just y still. But we can break this apart. And that's going to be equal to pt of x with I minus pt of y plus, and I didn't give myself enough room there, so that goes. We have pt of x with the projection onto t of y, and we've already shown that that's equal to 0, and so we now get that's equal to pt of x with the orthogonal projection of y onto t. Okay, so Pythagoras had something to say when you have orthogonal signals, and so we can bring that into play. So I'll change color just to keep it lively. So if x of s is the norm, is the induced norm. Now which norm is induced? Well, I don't know. It depends on what you defined as your inner product. But whatever it is associated with your inner product, however we ended up defining that, then let's see, then by the Pythagorean theorem, we're going to have x s squared is equal to pt of x s squared plus I minus pt of x s squared, like that. Okay, how would we do this? How would we go about proving this? Basically, I'm not going to walk through it right now, but it's a direct application of what you've seen above. Okay, so that's the projection operator. Now, let me just pull up one example before we quit. So let's say S is equal to R2, and T is equal to the span of one zero. So you can convince yourself that's a subspace of R2. So what projection operator would take us down there onto from S to T? So PT could be, actually let's put it this way, defined by the matrix. Let's see, we'll have some X, and we want that to be, whoops, with a 0 down below. So we'll just multiply this on the left by 1, 0, right, and below by 0, 0. And so that'll give us what we want. So it's PT is then defined by that matrix. So if we had some X and we wanted to project it onto the subspace T, given X, X hat is going to be this projection matrix times X. That just zeroes out the second row. Well, if that's true, then we must also have that we could project the result onto X as well. And is that indeed the case? So yes, this here, when you do that matrix product, you get a 1 here, 0, 0, 0. And so we have this nice easy matrix demonstration that our projection matrix, our projection operator as a matrix, we've come up with a matrix that where the product of the matrix with itself is equal to itself. So this seems kind of almost trivial in this particular case. Another trivial case is the identity matrix. The identity matrix squared is equal to itself. But what happens if we are projecting this onto some subspace that is, say, not following one of the axes? Then we're not going to have this really sparse-looking matrix, but we will still have a matrix where it multiplied by itself is equal to itself. And it gets kind of interesting. However, since I'm making up this example as I go, I'm not going to make up another example because I might make a mistake, and this is being recorded and my great-grandchildren will laugh at me. So let's call it good for today, and next time we'll talk about more about subspace projections.